Alright, let's do some cost minimization problems. Now there are a lot of ways you can solve these. You can use some fancy calculus methods. There's one called the Lagrangian multiplier method. I have other videos where I go through that if you're interested, but for this class, I just like to do it the simplest way you can possibly do it. Let's, at the very beginning, get a visual, graphical way of understanding what we're doing here. Let's look at our production function that we're going to be using today. So we're going to be looking at Q equals 50L to the 0.3 times K to the 0.6. So a Cobb-Douglas production function here. And let's assume that the cost of labor, the wage, is $5 per unit, and the cost of capital is $20 per unit to start. So down here I have a map of the Isoquants, and we're putting labor on the x-axis, capital on the y-axis. And so what we want to do, if the goal in this first problem is to produce 1,000 units of output, we want to find that Isoquant for 1,000 units, and that's this one right here, this green one. So 1E003 means 1 times 10 to the third, or 1,000 units. And so that's this one that runs right along here in our Isoquant map. Our goal is, given that the price of labor is $5 per unit and the price of capital is $20 per unit, to find, out of all these different possible ways to produce 1,000 units, which one is the cheapest. Now, a graphical method for solving this is to say, okay, what is a budget line going to look like? Not one particular budget line, but in general, what are all budget lines going to look like? We're going to be solving a couple of different problems here. Here are what our Isocosts are going to look like. We used to call them budget lines when we were doing utility analysis. So the blue one here is going to be what an Isocost looks like that has a slope of -1/4. It's going to be $5, which is the price of the labor, divided by the price of capital, 20. And so that slope of a budget line is the price of the variable on the x-axis divided by the price of the variable on the y-axis, and so that's going to be this blue line. So we can just drag it around anywhere, keeping the same slope. And so what we want to do is look at our green Isoquant here. Let me zoom in nicely so we can see that. So look at our green Isoquant, and we want to move this Isocost around until it's just barely tangent, because as we move this Isocost lower and lower and lower, that means we're using less and less labor and capital, and our cost is going down. So we want to move it down until we find a point where it's just barely tangent at one point. And from looking at this, my initial kind of guesstimate about how much labor and capital this would be is it looks like it would be somewhere in the neighborhood of 45 workers. And over here on the y-axis, maybe 21 or 22 units of capital. So what we're trying to do when we find a tangent point is we're trying to find a point on this Isoquant where we're getting 1,000 units of output, where the slope, if it's just tangent at one point, the slope of the Isoquant is going to be equal to the slope of the Isocost. So our two equations for solving this kind of problem are going to guarantee those two things. Number one, it's a point on this Isoquant where we're getting 1,000 units. Number two, that the slope of the Isoquant is equal to the slope of the Isocost. Now, I take time in every video to go through why the equations are what they are, because I think it's a whole lot easier and better to understand the equations than simply to memorize them. So now that we understand what we're going to be doing, let's go set up the equations and knock them down. So again, here's our production function, price of labor and capital. We need to produce 1,000 units as cheaply as possible. Now before we get going, let me just mention that what we're doing here would be called a long-run cost minimization problem, because we're assuming that both of our inputs are variable. We're long-term planning. Okay, if we need to produce 1,000 units of output every day, what is the optimal amount of capital and labor? At the bottom of this handout, we'll do a short run problem to see how that differs when we're going to assume we have a fixed amount of capital. That kind of problem is actually much simpler. So here, since capital and labor are variable, we have two variables that we're going to use in our solution. So our first equation is going to be the one that guarantees that the slope of the budget line, or slope of the ISO cost, is equal to the slope of the Isoquants. The slope of an Iso Quant is the marginal rate of technical substitution. And since we have a Cobb-Douglas production function here, we can use our shortcut rule. The marginal rate of technical substitution for a Cobb-Douglas is just the exponent on the x times y. So that's going to be 0.3 y, but here the y variable is capital, divided by the exponent on the y-axis variable, 0.6, times the x-axis variable, labor. So this equation tells us at any point on the isoquants what is the slope. And now we need to know what's the slope of the budget line. The slope of a budget line, an ISO cost, is always going to be the price of the x variable divided by the price of the input on the y-axis. So it's going to be, like we saw before, W over R, 5 over 20. Now yes, both of these slopes are actually negative, but since they're both negative, let's just go ahead and skip writing down the negatives and getting rid of the negative signs. They're going to cancel anyway. Now what I always like to do is go ahead and simplify this from the outset if it looks like it's easy to do, just to save us a little time later. 0.3 over 0.6 is the same as 3 over 6, which is the same as a half. So we could rewrite this as 1k over 2l, or just k over 2l. And then that's equal to this slope, which is a quarter. 5 over 20, 1/4. And what we're going to eventually want to do is solve this equation for either k or l so we can substitute it. Let's solve it for k. So multiply both sides of this equation by 2l, and we're going to get k equals 2l over 4, or 2/4 l, which is simply going to be 1/2 l, or 0.5 l, however you want to write it. Okay, so there's our first equation. It says that with this production function and with the prices that we see, our optimal combination of capital and labor is always going to involve us using 1/2 as much capital as we use labor. So if we're using 10 workers, 0.5 times that, we'd use 5 machines. All right, let's set up our second equation. The second equation simply guarantees that we are somewhere on that isoquant where we're producing 1,000 units of output. So we just set Q equal to 1,000 and set that equal to our production function over here. 50 L to the 0.3 times K to the 0.6. And all we're going to do is be substituting in K equals 0.5 L in here for K. Now again, just to simplify things slightly, let's go ahead and divide both sides by 50 just to minimize the number of moving parts we have in this equation. 1,000 divided by 50 is going to give us 20. And so here we have 20 equals L to the 0.3. And let's go ahead and make this substitution. 0.5 L goes in for K. So 0.5 L, all raised to the 0.6 power. And what we're going to do is distribute that 0.6 power to the 0.5 and the L. Let's go ahead and take care of that. 0.5 to the 0.6 times L to the 0.6. And now we just need to collect everything and solve this for L. So we're eventually going to want to divide both sides by 0.5 to the 0.6, whatever that is. And then we're going to want to collect those two L's. So how many L's do we have? L to what power? Right, L to the 0.9. When we divide 20 by 0.5 to the 0.6, I get something around 30.31. and that's equal to L to the 0.9 power. And then, as usual, we need to raise both sides to the 1 over 0.9 power, and that'll give us L. And when I do that, I'm getting something around L equals 44.3. And then to figure out how much capital we use this equation over here. We're going to use half as much capital as labor. So multiply 44.3 by a half, and that gives us about 22.15. Now, in addition to just finding out how much labor and capital we're going to use, one of the really important things we're going to want to focus on when we're analyzing a business's production and costs is to calculate how much would this cost the business to produce 1,000 units. And this is where we plug these values into, in what we'd call in utility analysis, the budget equation. In the analysis of the firm, we're going to call it the total cost equation. So total cost is just going to be $5 for each unit of labor times $20 for each unit of capital. $20 times 22.15 plus $5 for each laborer, 44.3. So that tells us that we're going to be spending about $443 on capital, plus we're going to be spending $221.50 on labor, for a total cost of $664.50. Now I break it apart like this because it lets us see something else that's important when we're analyzing the firm. Most of the time, we're going to be thinking, at least in the short run, about capital as being a fixed cost. And so if we were planning for the long run, but then actually thinking about how we would operate on a daily basis in the short run, then we would call this $443 our fixed costs, if that's the input that takes longer to adjust, and we would call labor our variable cost here. So fixed cost plus variable costs equals total cost. The last thing I want to calculate here is average total cost, or cost per unit. That makes it a lot easier to compare how much these things we're producing actually cost us, especially if we're thinking about doing different output levels. So average total cost, we just take the total cost, $664.50, divide it by how many we're producing, which is 1,000 units, and our cost per unit is going to be about 66 or 67 cents each. So average per unit cost. Okay, something else we need to think about as we're solving these problems. I like to go back and think about the pieces that we're putting into these equations. What is the marginal rate of technical substitution at this point? So what I'm asking is, when we're using 44.3 workers and 22.15 units of capital, let's go to our graph and look at that. And let's label this solution. So just looking at our graph earlier, we said we thought we would probably be somewhere around 45 units of labor, and we were right. It's 44.3 and about 22.15 units of capital. So let's label those points in our graph. We also know that this Isocosts line here is the Iso cost for $664.50, right? Since that was our total cost. So the Iso cost just shows us all the ways we could spend $664.50 on inputs, and the one right here is the combination that gives us the highest amount of output for that total cost. So you can think about this problem we just did two different ways. First, we could say we're trying to maximize the output for a given total cost, or we're trying to minimize the total cost for a given amount of output. The second problem is what we really did, since our problem was trying to guarantee 1,000 units of output. However, we could, if somebody gave us a budget of $664.50, we could solve this problem the other way and find that we could maximize our output at 1,000 units with that kind of budget. But the question at hand is, what is the slope of the Iso Quant at that point? Now, if you were paying attention earlier, you can already answer this question. Remember that this red point is where the slope of the isoquant is equal to the slope of the isocost. And remember, what is the slope of that isocost line? A quarter, right? Minus a quarter, but okay, a quarter. And so what does that slope mean when we're talking about the isoquant? Well, the marginal rate of technical substitution tells us that right at that point, if the slope is 1/4, it tells us that if we lost one machine, let's zoom way in here as much as we can, that at that point, if we lost one machine and we went down from 22.15 to 21.5, if we lost one machine, how many workers would we need to make up for that one lost machine? Well, if the slope is a quarter, we're going down 1 and over 4. So we would need 4 more workers to make up for that lost machine. On the other hand, what if we had one worker not show up? How many more machines would we need to make up for that one lost worker? 1/4, right? So if we got one more worker, we could give up a quarter of a machine. If we lost one worker, we'd need a quarter more machines. Or we could go with the 1 over 4. Lose one whole machine, need 4 more workers. If we lost 4 workers, we'd need 1 more machine. And the other question I have here on the handout is, what is the slope of the isocost line? Well, that's also a quarter at that point. And what does that mean? Well, that 1/4 just tells us that laborers cost 1/4 as much as capital. Sometimes we call the slope of that isocost the marginal rate of transformation. Let me write that down here. The marginal rate of transformation just tells you at what rate you can substitute between two inputs given their relative costs, keeping the same budget. So it just describes how we move along a given isocost. So if I only have a certain amount of budget, if I want to buy one machine, if I want to go up one, I have to give up 4 workers if I want to keep my budget constant. On the other hand, if I give up one machine, I could afford to hire 4 more workers if I wanted to keep the same budget. So marginal rate of transformation, slope of the isocost. All right, let's solve one more problem. Let's see what happens if the wages go up. How does our optimal choice of inputs change in the long run, assuming that we have a long enough time to where we could substitute capital and labor? Suppose there's a new law passed, and this new law increases the minimum wage in a country to $10 an hour from $5. Now let's resolve the same problem that we did before. Okay, let's see which pieces from the above problem that we can reuse so we don't have to start from scratch. All right, what about this part, the marginal rate of technical substitution piece? Is that going to change just because the price of labor went up? No, it's not. It's going to stay the same. So let's copy that piece down. Now, what about this piece over here? The wage rate divided by the price of capital. Yeah, right there, that 5 is going to change to 10, but the price of capital is not changing. So we're going to have equals 10 over 20. The slope of the isocost line is going to change. And again, we can simplify that, and we see, just like we did before, that the 0.3 over the 0.6 is just like a half. So we could write that as k over 2L equals 10 over 20. Also, that's the same thing as a half. Are you seeing what I'm seeing? We can just multiply both sides of this by 2. And what are we going to end up with? K over L equals 1, or K equals L. There are other steps you could go through to find the same answer, but what this is telling us is we're going to be using the same amount of capital as labor now that the price of labor is higher. Before, we were using twice as much labor as capital. Now, what about our second equation? that's just going to be the exact same as it was before. 1,000 units is what we need to produce, equals 50L to the 0.3 times K to the 0.6. All right, so let's set up that second equation. 1,000 equals 50 times L to the 0.3. And let's go ahead and make this substitution. K equals L. So let's just write, instead of K, L to the 0.6. And so just like before, let's divide both sides by 50. And we have 20 on the left-hand side equals L to the 0.9. Raise both sides to the 1 over 0.9 power. And here I'm getting somewhere around 27.9. So our solution, L equals 27.9. And how much capital are we going to use? K equals L. So same thing. K equals 27.9. Okay, let's try to verify this using just a visual check real quickly. Over here, before I started this video, I graphed this red line, which has a slope of 1/2, which is our new marginal rate of transformation. Slope of that budget line or Iso cost, same thing. And so again, if we try to move this Iso cost closer and closer to the origin, but we still have to be able to reach that green Iso Quant of 1,000 units. Okay, somewhere right around there. If we zoom in, my guess would be that our solution would be somewhere around right here, between 25 and 30 laborers, and about the same on the capital axis. But we know the solution now, right? It's 27.9. So let's graph that point right here. 27.9, I'll call it about right there. So here comes the common sense question of the day. What happens when the price of labor goes up? If there's a minimum wage, what should we expect to see in the long run? Well, we should observe businesses substituting, using less labor and more capital instead, right? So some people are going to be losing their jobs and being replaced with machines. This is a standard economic forecast for when the price of labor goes up. Now let's do some other comparisons though. Let's compare the total cost here. So our total cost is going to be multiply the number of workers times $10 each now, multiply the number of units of capital times $20 as always, and figure out how much our total cost is going to be now. I'm getting about $837. This also should make sense, that if we assume that businesses need to keep producing the same amount, maybe they have a contract where they have to still deliver 1,000 units, regardless of whether the cost of their labor went up or not, then it's going to cost more to produce the 1,000 units now that the price of their labor has gone up. So 837 now compared to about 664, 665 before. How about our average total cost now? Our cost per unit, of course, has to go up as well. Total cost divided by 1,000, our quantity, and now each unit is going to cost about 84 cents each, right? Not quite, but almost 84 cents each. Let's do one last question on this handout, and then this video is getting long enough, and we'll come back and finish it in a second part. How could we draw the demand curve for labor? So what is a demand curve? Well, any demand curve is just illustrating the law of demand. Ceteris paribus, what happens when the price goes up? So what we would want to draw is we have two prices of labor and two quantities. We see here that the wage, and here's the amount of labor. When the wage was $5 per unit, companies wanted to hire 44.3. So at $5 each, we'll call that 44.3 units of labor. And then when the price of labor went up to $10, they only wanted 27.9. So we can illustrate the demand curve for labor just by drawing a line through those points, although in reality it's probably going to be a curve. And we could do lots and lots of additional problems here at a wage of $7.50 and $15 and $20, and we could get more and more points to illustrate what this demand curve for labor would look like at different values. So in the next video, we'll come back and we'll look at an expansion path to see how our solutions change as we increase the amount of production, holding everything else constant, the price of labor and the price of capital. And then we'll look at a short-run cost minimization problem, assuming that the amount of capital is fixed. What happens to our required amount of labor? So I hope you join me for that. And if you have any questions about this, please let me know. Otherwise, I wish you have a great day, and I'll talk to you later. Bye-bye.